Good evening all of you, and here is the problem as you have already seen on thumbnail. So for every positive integer n, so n is a natural number, let's denote C of n as number of points which have integer coordinates and lies inside the circle x square plus y square equals n square. So what is Cn? It is number of points having integer coordinates which lies inside this circle given by x square plus y square equal to n square for every n, right? Then we have to find limit n tends to infinity, the number of such integer point divided by n square. It's very interesting questions. Before I go and do it, let's have a feel of the question itself. So let's say if I keep n equals 1, then the circle equation reduces to x square plus y square equals 1. Under that case, you can count manually. Up यहाँ पे clearly you can see how many such points are there, right? कैसे? Because we'll have one origin, other integer point 1 0, 0 1, minus 1 0, and minus 0 minus. There is no other point because at 1 you will get, it will be outside the circles. So if I ask you how many integer points are there strictly inside the circle, so it is 1. So here value of C1 is going to be 1. And I have kept n equal to 1. So hence C1 by 1 square for this sequence is going to be 1. Let's try for n equals 2 before I go and hit on its head for infinity, like for larger cases. So n2 will give x square plus y square 4. And it's not difficult to draw the diagram. So let me draw the proper sketch of this. And now we have 0, 1, 2, right? 0, 1, 2 over here. So let's count the number of integer point in first quadrant first, because by symmetricity we can exactly count in the other quadrant as well. So in the first quadrant we have 0, 0. 1 is always an origin for all this question. 1, 0. Now if I'll put x as 1, the value of y, so y square is going to be 4 minus 1, y is plus minus root 3. Okay, so at 1 the value of y which we'll get is root 3, right? So it is clearly lesser than 2, but it's not more. So at 1 we'll not get the output as integer, right? So here we'll have 1 comma root 3 which is inside, which is exactly on the circle, and root 3 is 1.71. So clearly we have only these points are integer. At 2 we'll have 2, 0. Similarly we have points over here 0, 1. And that's it, right? So if you'll see, the number of points which is strictly inside this is going to be, because 0 in the first quadrant, 0 in the second quadrant, 0 in third quadrant, and 0 in fourth quadrant, right? The only point that I am having is on this axis. So we have 1 over this, 2, 3, and 4. So total number of integer point is 4 plus 1, which is 5. So in this case, C2 is going to give me 5 divided by 2a square. So 5 by 4 is 1.3. Along positive y-axis, we have 0.1, 2, and 3 over here. Now at x equals 1, if we'll check x square plus y square equals 9. So that shows as x equals 1, 1 plus y square will be 9. So y is going to be 9 minus 1, which is root over 8, right? Okay, so root 8 is 2 point something. So the possible value of y can be 1, 0, 1, 1, 1, 2, and 1, root 8. So clearly corresponding to x equals 1, we have got 3 point over here. Similarly, we can try with x equals 2. So that will give y square equals 5. So y equals root 5, which is again 2 point something. Okay, so we have 2 point something over here. So possibilities is again 2, 1, 2, 2. Is clear? At 3 I have only 1 point. So the number of lattice point or the points having integer coordinate is 1, 2, and 1 over x-axis, right? So we have 3, 2, 5, and 1, 6 over here in the first quadrant. So in the first quadrant, I can count, yeah, 6 members over here on or strictly inside. right? If you want strictly inside it, like not on the circumference, then we are going to have 2 on this side, the y-axis, right? So here we'll have 3 and 3, 6. 6 here, exactly y symmetricity. Similarly, we'll have 4 points over here and 4 points over here, right? If you want to count inside, because the way we are counting is strictly inside we have 4 points, so 4 into 4 in each quadrant. On the positive x-axis we have 2, so that will be reflected on the positive y-axis. Similarly, negative y-axis or negative x-axis, so that will give me extra 4 into 2, right? If I am leaving the points on the boundary strictly inside, so 16 plus 8, which is 24. So again you can count, it's 24, which is C3 divided by 3a square, which is 9. So again we have almost it's 2 points something. So this is the way the series goes on, and we need to find the number of lattice points when n is really large, and that ratio Cn by n square. So by now you have already understood, like if given a circle of radius n, clearly 0, 0 will be a point inside it. Now corresponding to x equal to 1 value, how many points will get over here? Okay, so there is a very nice way to count this, because the circle equation is x square plus y square equals n square, where n is a natural number. So y square is going to be n square minus x square. Now if the value of x is at 1, I'll get n square minus 1. So y is root over n square minus 1. And now you see, if we'll try to see the greatest integer of root over n square minus 1, so that's an integer, because I want to count the value of y starting from 0, 1, 2 till lambda, right? Such that lambda is the maximum integer. Lambda is in maximum value of that is lambda will be less than equal to root over n square minus 1, right? So it will go up to greatest integer of root n square minus 1. That is perfectly integer. If n square minus 1 is a perfect square, then I'll get point on the boundary. If it is not a perfect square, then automatically it will count all the points. Okay, strictly above x-axis. And if you want, you can include the x-axis point as well, right? So corresponding to now any point x equal to k, at any input x equal to k, I know how many points will be there strictly inside this, and we can separately include this k comma 0 as well. So that will be nothing but actually number of points, which is integers which are lesser than n square minus k square. Okay, so this floor function of this, or greatest integer of this, will tell me the number of counts. I hope this is quite clear for all of you. So from here, I can tell has denotes, let's say, number of points x comma y, such that at x equal to k, I want y to be integer, and of course positive integer at n equal to 0, and at the same time x square plus y square is less than equal to n square, and this count is going to be nothing but greatest integer of n square minus k square, right? For k dancing from 1 to n. So k can dance from 1 to 3 to. For k equal to n, we are already counting these points also, right? The point on the axis. Okay. Now the number of points, the number of count which is there in the first quadrant is going to exactly same as number of count in the second quadrant and third quadrant and fourth quadrant. Of course, you can add this number of points on the axis separately if you want to do so. Right, so the total number, so the value of sigma that I am going to have is sigma greatest integer of n square minus k square, 4 times of this, because in each quadrant, and I have to incorporate origin as well, so plus 1 into picture, right, where k is running from 1 to n. So this is my expression for Cn, and what I need is Cn by n square calculation, limit n tends to infinity. Now this is not very tough, guy, because we know greatest integer of any function x will be lesser than equal to x, and will be more than equal to x minus 1. This is by definition, right? In fact, here inequality will be strict on the other side. This is because greatest integer of 2.5 is going to be 2. Greatest integer of 3 is 3. Right? So you know the basic definition. From there I can write greatest of n square minus k square will be less than equals n square minus k square. And that will be greater than n square minus k square minus its root, because I'm interested in root of this quantity. Sorry, I'm interested in root of this quantity. Certainly between root over n square minus k square minus 1. And now we know, since root over this quantity is definitely more than root over n square minus k square minus n, right? Because this quantity is little bit lesser than n for any k except k equal to n. In that case that will be 0. So for any k this quantity is going to be negative. So it's definitely greatest of root over n square minus k square is less than equal to root over n square minus k square and is strictly greater than n square plus k square minus, because n square k square may say if you subtract something lesser than 1, definitely that will be strongly lesser. Right, now this is very fantastic, because from here what I can do is we can divide by n square. That's precisely our question, right? Because we need to take sigma of this and divide by n square. So let's take sigma of this quantity, n square minus k square is less than sum over. So precisely I'm writing k equal to 1, 2, 3 and we are adding all these equations. So we'll get this sigma n square plus k square minus n. K is running from 1 to 1. Right? And this by n square. So we'll divide by positive quantity, the sign of inequality will remain invariant. Now let's take limit n tends to infinity. Limit n tends to infinity. And by Sandwich theorem, first I'll try to evaluate this and then we'll try to evaluate this. Now the first one, you know, it's limit as integration of sum. So this quantity can be written as root over 1 by k by n whole square. So there I have managed to keep 1 by n outside, and it's sigma of this where k is running to 1 to n. Limit n tends to infinity. And very soon you can identify this as a Riemann sum, where the sigma will be converted to integral and k by n is substituted as, let's say, x. That gives me 1 minus x squared dx. 1 by n is replaced with dx. As n tends to infinity, k by n goes to 0. So k equals 1. So at k equals 1, we have 1 by n equal to x. And limit n tends to infinity, so lower limit goes to 0. The upper limit as k tends to n, so we have n by n. Limit n tends to infinity, that goes to 1, so upper limit is 1. So this is precisely 0 to 1 integral of root over 1 minus x square. And that either you can use integration by parts with 1, or you can easily feel it's 1/4 of the circle, because root over 1 minus x square is coming from the circle equation, unit circle. So this area is precisely the geometrical meaning of this integration, and it's nothing but pi over 4. So I know this evaluates to pi over 4. Now what about LHS? LHS, again we can little bit manipulate this to be pi by 4. Similarly, you can use Sandwich theorem over here, and you'll get this also going to be pi by 4. Hence the final answer for this question, this entire limit is going to converge to a value pi by 4. And that was quite a beautiful question, because you can clearly see the sense of it, because as the n value increases, the area of triangle, as the n value increases, the area of circle becomes almost pi n square. And the number of points there is, like if you see the total number of lattice pointers in the limiting sense. So it's pi n square, and the number of lattice points is almost equal. Of course there is huge gap, but you can see like the number of points is same as number of points in the square, and which is going to be this square of side n to n. So it's like 4n square, and that goes roughly to pi by 4. So that makes very crude sense of it, but actually you have proved in the limiting case approximately, like 1/4 of the area of unit circle will be the density of the lattice points. So thank you. Have a good day. I hope you have enjoyed.